Now we go to the second talk. I am happy to introduce you speakers, Vyacheslav Yukalov, and this is, as I understand, joint talk by Vyacheslav Yukalov and Елизавета Yukalova. And they spent a few years here in the that time International Center of Condensed Matter Physics at the end of the past century. And actually, I visited this building for the first time when I was for the first time in Brasilia and met Flava and Lisa here. So possibly they can see the same auditorium. That time there was much less posters on the wall, okay, but the rest more or less the same. So I'm happy to introduce you, Professor Yukalov, and his talk entitled, I will have to read, uh, something about regulated spin dynamics of dipolar and spinor atoms. Okay, please, Slava, you can speak.
Thank you very much for the introduction. I would like to thank Victor Dadonov for inviting me. And I would like to say that we wishes to Victor and we are happy to participate in this event devoted to his jubilee. I'm going to talk about dipolar and spinor atoms. Nowadays, there are many of atoms and molecules that can be confined in traps of different geometry, including the so-called optical lattices created by laser beams. The plan is as follows. I will say several words about the cold atoms and the Hamiltonians they are described, and uh, what magnetic field produces there, what is the picture for the case of an insulating lattice, how it is possible to describe the equations of motion, and by these, how it is possible to regulate the spin dynamics in these systems. And at the end, I will mention that this is not only the problem that is of interest by its own, but it can be useful for creating different memory devices. Cold atoms are usually described by angular momentum, that is shown here, where m is the magnetic quantum number. Therefore, field operators are the columns in the space of this magnetic number. And if we are working with an optical lattice, then it is possible to expand the field operator over Wannier functions. The overall system Hamiltonian consists of several terms containing the single particle term where there is no magnetic field. The role of magnetic field is in additional terms that describe the linear Zeeman interaction, and also in atoms there is the so-called quadratic Zeeman term. Then there are the terms describing local interactions and long-range dipole interactions. The linear Zeeman term has the standard form where mu is the magnetic moment of an atom, B is an external magnetic field, and as I told, there is an additional quadratic term responsible for the quadratic Zeeman effect, which consists of two parts, the static current quadratic Zeeman term and alternating current quadratic Zeeman term. The corresponding parameters describing these terms of the quadratic Zeeman effects here, where this is the hyperfine energy splitting, nuclear spins, here Rabi frequency, and the tuning from internal transitions like spin transitions or hyperfine transitions. Local interactions are described by the local potentials written here. They are called local because they are proportional to the delta function. And here is the matrix elements of this local interaction. These interactions are characterized by scattering length of atoms. And in addition, there are dipolar interactions of long-range type, as is shown here. And in general, this is the standard part of the dipolar interactions. And in the general way, it is possible to regularize them in order to remove some artificial divergences in the terms. And this regularization is connected with taking into account the sizes, finite sizes of atoms and molecules, so this term, and the screening effects, the last term. So this is the most general form of the dipolar interactions. The very specific feature of the setup we are going to consider consists in the following. We not only have the system of atoms having spins, and it would be possible to act by external fields on these magnetic moments of the atoms. But in our setup, we make make it more general. We have here the sample, which contains magnetic moments of atoms, and this sample is inserted into the magnetic coil. That is the part of the electric circuit. So in addition to an external magnetic field on the system, we have in this setup an additional field created by the system itself. As soon as the spins of the system start moving, they create an electric current over this lattice, and there is an electric current through the electric circuit, and the electric current produces an additional magnetic field in this perpendicular direction. This is called feedback field because in this setup it is created by the system itself. Why do we need this additional complication of the whole setup? This is because we connect on the system not only by brute force, by imposing external magnetic fields, but we can force the system to adjust better to the motion by creating a feedback field. The role of feedback field is in collectivizing the motion of atomic spins inside the system and forcing them to move faster. So it is a very useful addition. The electric current that starts circulating around the magnetic coil can be described by the Kirchhoff equation. In turn, this electric current is connected with the feedback field, and it is possible to reduce the Kirchhoff equation to the equation describing the feedback field created by the electric circuit. Here, gamma is the attenuation of the electric circuit, omega is the natural frequency of the electric circuit. And the electromotive force is created by spins of the system themselves that are given here. For the case of an insulating lattice, we can expand the field in operators over Wannier functions and can take into account that the transitions between different lattice sides are suppressed. Then we can introduce the local spin operators associated with the corresponding lattice sites, J here, and the local density of atoms in each lattice site. It is worth noting that this representation is valid for any statistics, either Bose or Fermi. After this, after expanding the field operators over Wannier functions, we obtained the single particle term described here. The term corresponding to the local interactions is specified here for the case of atoms with angular momentum 1. Although it is not very important, it's just to understand the general structure. The most important for the following purpose is that this local interaction terms is usually it does not depend on the direction of spins. So these parts can be a bit different, but the main is that it will not influence the spin motion. And these are the terms corresponding to the linear Zeeman part and the quadratic Zeeman term, containing these two parts. Now, this is the total magnetic field, which consists of an external field, a constant magnetic field, a regulated magnetic field, and feedback magnetic field. In addition, we have the interaction. As far as there are spins on the system, there exist also dipolar interactions that take this form. After this, we need to find out the equations of motion for the spin operators. These are found by the usual procedure of writing down the Heisenberg equations of motion. And remember the form of the Hamiltonian, we see that the single particle part does not influence the spin motion, as well as the local interactions that are rotationally symmetric with respect to spin, they also don't influence the spin motion. So only the parts that contain spins influence this spin motion. And this is the linear Zeeman part, quadratic Zeeman part, and dipolar interactions. After obtaining the equations for the spin operators, we need to pass to the averages. In averaging, taking into account the dipolar interactions for different lattice sites are of long range type, it is possible to use this kind of decoupling. However, it is important that because of the quadratic Zeeman effect, we obtain here these additional binary forms corresponding to the same lattice site. And these terms cannot be decoupled in the usual mean field way. So we suggest to use the generalized decoupling of this form, and this generalized decoupling is exact for spin 1/2, and it is asymptotically exact for large spins. Then we have to choose the method of solving the equations. There are several possibilities. One, to use the quasi-classical approximation, which actually, after averaging the equations of motions and use the mean field approximations or generalized mean field approximations, reduce to the equations for classical vectors describing average spins. This picture is good from the point of view of techniques, because after having the equations, although complicated, for average spins, we can push all this stuff into a computer and just directly solve the equations of motion for the average spins. This description also good when we are dealing with coherent motion of spins, especially with large spins. But it is bad from the point of view that it doesn't describe the initial stage of the motion, because this is good for the coherent motion of spins. But at the beginning, when spins yet are not moving and only start moving, there is no coherence in the system, and all motion is triggered by spin waves that exist in the spin system. And this initial stage cannot be described in the quasi-classical approximation. In order to describe the overall process from the beginning till the part connected with coherent motion, we use the scale separation approach. We also used the quasi-classical approximation and compared the stages in time that correspond to coherent motion. There is a good correspondence, but as I already told you that the beginning part of the process cannot be described in the quasi-classical approximation. In this case separation approach, we introduce the several convenient functions that can be related to measurable quantities of the system. This is the transverse polarization, coherence intensity, and spin polarization along the axis Z. In addition, there are very cumbersome quantities describing fluctuations responsible for spin waves. I don't write them here, not to make the presentation too cumbersome. Then we pass to dimensionless quantities, like, for example, feedback field dimensionless, which is normalized to the attenuation rate that describes the coupling between the electric circuit and the spin system. And this is the attenuation responsible for the interaction of spins. Then we have in the system equation several attenuation parameters: attenuation of resonance electric circuit, attenuation describing the coupling, attenuations corresponding to spin interactions, and the part of attenuations related to spin waves. All these attenuations in practice are small as compared to Zeeman frequency. Therefore, it is possible to classify the cumbersome system equations which we obtained, separating their the fast variables like the dipolar polarization and perpendicular to the axis Z part, the feedback field, and the slow variables describing coherence intensity and spin polarization along the axis Z. Spin fluctuations are also fast variables. After this, the procedure goes as follows. We solve the equations for the fast variables, while the slow variables are treated as quasi-integrals of motion. Then substitute these solutions of fast variables into the equations for slow variables, and then average the right-hand sides of equations for the slow variables over time and random fluctuations, as is shown here. As a result, we obtain rather cumbersome equations. Just look at them and forget them. And in addition, here we have the parameters alpha and beta, which are actually not constants, but that are functions describing the coupling of the magnetic system with the electric circuit. What is important here, it's possible to pay attention only to this effective coupling parameter describing the coupling between the system of magnetic moments and the electric circuit. The existence of quadratic Zeeman effect turns out to be similar to the existence of an anisotropy term. It consists of two parts, static current quadratic Zeeman effect and alternating current quadratic Zeeman effect. The existence of these parts leads to the following. Actually, the strong relation between the electric circuit and the magnetic system occurs only when there is a resonance between the effective spin motion and the frequency describing the effective spin motion and the Zeeman frequency. But it turns out that equations of motion, the effective frequency of spin motions, is composed of these parts, which contains the anisotropy terms due to the quadratic Zeeman effect. Because of this, there is no possibility of making exact resonance on the system, since this part contains the spin polarization which changes in time. So all these changes in time so that the detuning is not small. For the partial solution of this problem, in order to make a strong coupling between the resonance electric circuit and the magnetic system, one way is to use this so-called the method of trigon resonance, which we suggest. The idea is simple. We need to have resonance. Then we need to make this detuning small. This detuning is presented through this sum. So it's possible to switch on this additional adjusted film so that at the initial moment of time to kill this part. So this is the condition of the trigon resonance. If so, then at the beginning moment of time, we will have resonance and the system will start moving. Why this is useful? This is useful because on this principle it is possible to create different memory devices. The idea is as follows. We keep the system of spins, for example, in a metastable state, however, which is frozen because of the presence of anisotropy term. At the time when we need to reverse a spin, then we make the trigon resonance and the system starts moving. By this way, we can keep the spins frozen for quite a long time and reverse them at the desired moment of time. This reversal, because of the feedback action of this transverse magnetic field, is very fast. It is possible to evaluate the different numerical parameters for several atoms that are used in traps. I will not enumerate, losing time, all these parameters. The idea is that it is possible to evaluate the influence of static current quadratic Zeeman effect and alternating current quadratic Zeeman effect. In the range and parameters, they both play the role, but it is easier to organize a situation so that the static current effect will be the most important. This is what is happening when we first do not use trigon resonance, just switch on the setup as is described above. Then, depending on the frequency of the resonance electric circuit, we will have these different types of motion, and the fastest here, that is the fastest possible way or reversing the spin, occurs when there is a resonance, when this omega is tuned close to the Zeeman frequency of the system. So this figure shows that the switching on of the quadratic Zeeman effect changes the dynamics of spins. And what is most important is that reversal time, because of the feedback field, is very fast. It's of this order, 10 minus 10 seconds. Also, what is very important using this trigonal resonance, we can start spin motion at any time we wish. If we wish to make this part at some moment of time small, then at this moment of time we switch on this additional adjusted field, which kills the anisotropy, and the process starts. These are numerical solutions for the equations for the case of trigonal resonance that is switched on at different moments of time. So what is good here is that we can regulate the initial moment of spin reversal. What is the defect here is that we arrange the exact resonance at the initial moment of time, but during the spin motion, this resonance is spoiled. And because of this, we obtain these long tails when there is no strict resonance. In order to remove these tails, we also use the method of dynamic resonance tuning, when the detuning can be regulated during the whole process so that to be small. This is obtained by regulating the adjusted magnetic field so that it would compensate this anisotropy term, or by changing the anisotropy term by itself using the quadratic Zeeman effect. Then making this resonance possible during the whole motion of the spin, we will have much faster reversals, and we avoid these long tails. Here the comparison of the trigonal resonance when the trigon part is working, and switched at the same time the second possibility of dynamic resonance tuning, when these tails are removed. In this way, we can make very fast spin reversals at different moments of time that we need. And I am going to conclusion. We suggested several mechanisms allowing for atomic spins polarized, and the most important, we can realize the spin reversal at a required time. This can be achieved by using the trigonal resonance, dynamic resonance tuning, and regulating the parameters of the quadratic Zeeman effect. Thank you for your attention.